Welcome to our journey into understanding tokenization in large language models. These models are sophisticated computer programs designed to understand and generate human-like text. They learn from vast amounts of data, recognizing patterns, grammar, and context. For a language model to learn effectively, it needs the text data in a form that balances detail with computational efficiency. This balance is achieved through tokenization. Tokenization is the process of breaking down text into smaller units called tokens. Tokens are the fundamental pieces that the model processes. They can be as small as individual characters or as large as entire words or phrases. The choice of how to tokenize text greatly affects the model's performance and efficiency. One straightforward approach is character-level tokenization, where each character is a token. For example, the word hello becomes A-E-L-L-O. While simple, this method has drawbacks. It produces long sequences of tokens for even short texts, increasing computational load. Alternatively, we might consider word-level tokenization, where each word is a token. The sentence, "I love coding," becomes "I love coding." This method captures words as meaningful units, aiding understanding. However, it presents challenges with vocabulary size. There are hundreds of thousands of words in a language, including slang, technical terms, and typos. Handling all possible words requires a vast vocabulary, making the model large and less efficient. To address these issues, we turn to subword tokenization methods like byte pair encoding, or BPE. BPE strikes a balance between character-level and word-level tokenization. It starts with individual characters and iteratively merges the most frequent pairs to form new tokens. This approach captures common subwords like ing, pre, or tien, effectively handling new or rare words by breaking them into familiar components. Let's see BPE in action with the word running. Initially, it's tokenized into characters R, U, N, I, and G. We find the most frequent adjacent pairs, in this case, and followed by N. Next, we merge I and an into N. Our sequence becomes R, U, N, G. By capturing these common subwords, we reduce the sequence length and help the model understand language structure. By applying BPE across a large corpus of text, we build a vocabulary that includes characters, common subwords, and even whole words. This vocabulary is tailored to the language patterns in the data. Frequent words or subwords become single tokens, while rare words are broken down into smaller known components. Consider a practical example with the word unhappiness. Using BPE, we tokenize it into unhappiness. Each token represents a meaningful subword. The model processes these tokens, learning their representations. When generating text, the model can combine these tokens to form words, even if it hasn't seen the exact word before. Beyond BPE, there are other tokenization methods like word piece and sentence piece. Word piece, used by models like BERT, builds a vocabulary of subwords focusing on maximizing the likelihood of the training data. Sentence piece treats the input text as a raw stream of characters without predefined boundaries, allowing for language-independent tokenization. Tokenization becomes even more critical with non-English languages. Languages like Chinese or Japanese don't use spaces between words, making word-level tokenization challenging. Subword methods like BPE are language agnostic and can effectively tokenize these languages by learning common character patterns. Modern text often includes emojis, hashtags, and other special characters. Properly tokenizing these elements is essential for the model to understand and generate relevant responses. BPE can handle these by treating them as individual tokens or learning frequent patterns involving them. The choice of tokenization method directly impacts model performance. Efficient tokenization leads to shorter sequences, reducing computational requirements and improving understanding. Tokenization isn't limited to natural language. It's also crucial when models are trained to understand programming languages. Code often includes indentation, symbols, and syntax-specific keywords. Advanced tokenization methods group spaces and recognize code structures, allowing the model to better understand and generate code. In practice, building an effective tokenizer involves several considerations. We must decide on the vocabulary size. A larger vocabulary can represent more subwords directly, but increases the model size. Including diverse and representative data ensures the tokenizer works well across different contexts and languages. Looking ahead, researchers are exploring tokenization-free models that process text as raw bytes or characters. These models aim to eliminate the need for tokenization, simplifying the pre-processing pipeline. However, they face challenges like longer sequence lengths and increased computational demands. In conclusion, tokenization is the essential bridge that allows computers to process and generate human language. By breaking down text into meaningful tokens, we enable language models to learn from patterns and data effectively. Thank you for joining us on this exploration of tokenization in language models. Keep asking questions and stay curious.